This is a video for MEI Core Pure Mathematics, Vectors 5, Further Lines and Planes, 5.5, the perpendicular distance from a point to a line in 3 dimensions. So given a point P, that's this one here, and a line L, that's this direction here, we want to find the perpendicular distance from P to L. The perpendicular distance is also the shortest distance. And sometimes we'll be asked for the shortest distance rather than the perpendicular distance. Notice we've got no formula for this. And consequently, we really need to think about what we're doing. So you need to think about the technique before we start. In fact, we're going to look at 2 techniques. One of them involves using the scalar product, and the other involves using the vector product. And let's have a look at those in a bit more detail. So the first method is using the scalar product. So if we've got a point P, that's this point here, and a line L, that's this line here, that's its direction vector, we want to find the perpendicular distance from P to L. We start out by identifying a general point, X, and establishing its position vector, OX. So this is the thing that we're interested in. The next thing is using P is to establish the vector Px. And again, that will be a general vector in terms of the position vector of x. And that's this line here. And then we use the fact that we want Px to be perpendicular to D to use Px.d equals 0. And that will fix the position of x so that Px is perpendicular to D. And then finally, we simply want the length of Px, because that would give us this length here. It's better to look at this with an example, so let's have a look at this one. So the first thing is to establish a general point on the line. So OX, the position vector of a general point on the line, will be 1 plus 5 mu, 13 mu, and 2 plus 3 mu. Px, so the line joining P to this general point, will simply be this vector OX, 1 plus 5 mu, 13 mu, and 2 plus 3 mu, minus P, 3, 1, minus 1. And if I take those away, I'll get minus 2 plus 5 mu, minus 1 plus 13 mu, and 3 plus 3 mu. And now I want to use the fact that I want Px to be perpendicular to this direction here of the line. So I want minus 2 plus 5 mu, minus 1 plus 13 mu, and 3 plus 3 mu, dot 5, 13, 3 to be equal to 0. So let's do the dot product. I shall get minus 10 plus 25 mu from the first bit, minus 13 plus 169 mu from the second bit, plus 9 plus 9 mu from the third bit, and I want all of that to be equal to 0. If I collect this together, I get that 203 mu minus 14 is equal to 0, which means that mu is equal to 14 over 203, which actually cancels down to 2 over 29. So the next stage in the technique is to take this value for mu and plug it into this expression for px. So I get a particular value for px, which is the vector which is perpendicular to the direction of the line. So my px will become minus 2 plus 10 over 29 minus 1 plus 26 over 29 and 3 plus 6 over 29. And if I take out the 1 over 29, I get left with minus 48, minus 3, and 93. And so the perpendicular distance is the length of that vector, which is 1 over 29 times the square root of 48 squared plus 3 squared plus 93 squared. And if we plug that into the calculator, we get a value of 3.61 to 3 significant figures. Now there's quite a lot of working on here, so we're going to look at solution slides spread across 2 slides. The first part is going to take me as far as finding the value of mu, and the second part will take me as far as finding the actual result here. So here's the first part of that solution. So here's where we get the general point x, and notice that is in terms of mu. And so px, the vector between p and the general point x, is here. And then we use the dot product to get this equation, and therefore the final value of mu, which fixes px perpendicular to the direction of the line. And we notice that this cancels down to 2 over 29. So following on from that, we know that mu is 2 over 29. So we plug mu into here, and therefore we end up with this for my vector px. And remember, this is the specific vector which is from p to the line and perpendicular to the line. And finally, to get the perpendicular distance, we just want the length of that vector, which is this calculation here, and comes out to be 3.61. Now, if you wanted not just the distance, but actually whereabouts on the line x is, you could just substitute mu equals 2 over 29 back into the equation for the line, and that would give you the point x. Okay, so method 2 uses the magnitude of the vector product. So if we have a look at the magnitude of A cross B, it's AB sine theta. This is the cross product definition up here, and you'll notice that it's missing the unit vector n, which is perpendicular to both A and B, and that's because I just want the magnitude. If you have a look at this diagram, here's my point P, and then this is a point on the line, and in particular it's this point here, the known point on the line. I want to get px, this distance, and that's just going to be AP sine theta, just using this right angle triangle. Now, AP sine theta comes from this. AP cross D will give me AP sine theta times the magnitude of D. So if I rearrange that, I'll get that AP sine theta, the thing I want, the length of AP times sine theta, is just this thing, AP cross D divided by the magnitude of D. And AP we know is P minus A, so we get this formula, P minus A cross D, magnitude of that divided by the magnitude of D. Again, it's easiest to see that with an example, and actually this is the same example as the one we use for method 1. So there's my point, and there's the equation of the line. This thing here is A, and this thing here is D. So we want P minus A cross D. Well, let's have a look at P minus A first of all. That's going to be 3, 1, minus 1, minus 1, 0, 2. And that just gives me 2, 1, minus 3. I then want to cross that with D, so P minus A cross D will give me 2, 1, minus 3 cross 5, 13, 3. And that gives me 3 take away minus 39 is 42. Minus 15 take away 6 is minus 21. And 26 take away 5 is just 21. And now I want the magnitude of that. And that's just the square root of 42 squared plus 21 squared plus 21 squared. This is 4 lots of 21 squared plus another one, so that's 6 lots of 21 squared inside the square root here, so that's going to be 21 root 6 when I square root it. Now the other thing I need is I need the modulus of D, and that's just going to be the square root of 5 squared plus 13 squared plus 3 squared, which is the square root of 203. My distance is going to be 21 root 6 divided by the square root of 203, which gives me 3.61. And again, that's to 3 significant figures. And there is that written up so you can follow it a bit more easily. Here's P minus A, and then P minus A cross D, and then finally the length of P minus A cross D. So that's the top line in our formula up here. And then the magnitude of D here, so that's the bottom line. So we just divide the two and we get the final result. So in summary, it doesn't matter which method you choose, whether you use the method 1, the scalar product, or method 2, the vector product, and it's really down to you as to which you prefer. This technique is a fairly simple formula. However, it's not in your formula book, so you'll need to remember it, and it may be that just remembering the diagram will be enough to remind you about how to construct the formula from there. The next video in the sequence is 5.6, the perpendicular distance between two parallel lines.